1, Hyperbolic Functions and Circular Functions. In this module, we will be focusing on identities and properties of hyperbolic functions, inverse hyperbolic functions, relationship between hyperbolic function and circular functions, separation of a given function, which involves terms containing both hyperbolic functions and trigonometric functions to real and imaginary parts. Let's start with hyperbolic functions. If we wish to express exponential function e raised to x as sum of both even and odd function, we can have e raised to x equals e raised to x plus e raised to minus x divided by 2 plus e raised to x minus e raised to minus x divided by 2. If you call this part as f of x and this part as g of x, you can observe that f of x and f of minus x are the same. Similarly, g of x and minus of g of minus x are the same. That is, f of x satisfies the property of even function because f of x equals f of minus x, and g of x satisfies the property of odd functions. That is, g of minus x equals minus g of x, or g of x equals minus of g of minus x. Thus, we have successfully splitted e raised to x to even and odd functions. We know that trigonometric cosine function is an even function. So this even part was given the name cos hx because this is not exactly cosine function. It's different, but it has a similar property to that of cosine function. That's why it is given the name hyperbolic cosine or cos hx. This part which satisfies the property of odd function was given the name sin hx because we know that trigonometric sine function is an example for odd function, and since this part satisfied a property similar to that of sine function, it was given the name sin hx or hyperbolic sine of x. Hyperbolic functions and circular functions have similar names not because they have exactly same properties. They differ in properties, but they have similarity in many properties. That is why they are given similar names. There exist many properties and many identities which are entirely different for hyperbolic functions when compared to trigonometric functions, but taking account of the similarities, they are given similar names. Having obtained the expressions for cos hx and sin hx, we can now define 1 by sin hx, which is equal to cosec hx, and 1 by cos hx, which is equal to sec hx, and tan hx and cot hx. We have cos hx equals 1 by sin hx, that is reciprocal of expression of sin hx. Therefore, cosec hx equals 2 by e raised to x minus e raised to minus x. Similarly, sec hx equals 1 by cos hx, which is equal to 2 divided by e raised to x plus e raised to minus x. Similarly, tan hx equals sin hx by cos hx, which is equal to e raised to x minus e raised to minus x divided by e raised to x plus e raised to minus x. Cot hx equals reciprocal of tan hx, which equals e raised to x plus e raised to minus x divided by e raised to x minus e raised to minus x, which can also be evaluated using cos hx divided by sin hx.